Hello, in this video we are going to look at the basics of summation notation, which is also called sigma notation. Sigma because, as you can see in this crazy looking notation, those letters, those Greek letters right there are called a sigma. Okay, the sigma in Greek. So you get the name sigma notation or summation notation because it is nice mathematical notation to help us sum up or add up a bunch of things. In fact, it helps us add up a bunch of terms in a sequence, in a pattern of numbers. So I'm going to break down the specifics of it, but let me look real quick at this one on the right. This is saying I have a sequence that's defined by that rule. So the first number is 2, and then you go times 2, and then times 2 times 3, and then 2 times 4, and it's saying only do the first 4 terms. 2 times 4 is 8, not 4. I think I should know that. And then this notation is saying add all of those up. So you get 6, 14, 6 plus 14 is 22, and that's the answer to that notation right there. It's saying take the first 4 terms defined by that rule right there and add them together. Okay, but let's break down the specifics of this, make sure we really understand summation notation. On the left, I have the general form of it. This is our sequence rule, okay, or the function, some might call it. So that will look something like 2i, or 2i plus 5, or 2i squared, or I factorial times 7. Okay, it can basically be anything you want, but it's going to have an I as the variable. Or more specifically, the variable in that sequence right there is going to match up with the variable right here. At least one of them, because this is what we call the index. That is the number that is changing with each term. So you see for this summation over here, in the example, our index starts at 1. So at first we let I equal 1 for the first time. But then for the second iteration, we go 2 times, now we change I to equal 2. And it's very important that you pay attention to what letter this is, because that is the letter that changes each time. There might be other letters or variables in your expression. There are times where you can come across a sigma where it's like 2i plus n. Or maybe, and this is kind of more common, you'll find 2i divided by n. In that case, it would be 2 times 1 over n plus 2 times 2 over n. So notice how the n is not changing, because according to the index, that is not what is varying. That is what the I is what's changing, the n is not. And you'll learn techniques of what to do with that n on the bottom. Okay, but it's just important, don't sum that. Now, I stopped at 3 on this top one, but I shouldn't. I should go one more to 2 times 4, because this is the index of I. The 1 is the lower limit, your starting point. The number up top is called the upper limit. It's the end point. So for this example, I start with I equal to 1. And that can be a different number. That's okay. That's just what you let I equal for the first time. And we stop when we let I equal 4. And then you just go through and you add your terms up. So you simplify 2. 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. And we go 6 plus 14, which is 22 like we saw before. So there we're running through the basics, understanding the basics of summation notation. So now we'll try 2 more examples where we can put it into action. Okay, here we go with these examples. And I threw in some different stuff with these. So in the first one on the left, it's a summation, and here's how you read it. The summation from I equals 0 to 7 of 1 divided by I factorial. So that's kind of how you read it. So we first do our first term. 1 divided by, what is the first thing that I should be? 0. So 1 over 0 factorial. Plus 1 over, now we up 1, we plus 1 to that I value. So it's 1 factorial. And then it's 1 over 2 factorial. And we're going to keep going and keep going and keep going and keep going until, what is our upper limit? 7. So we go all the way until I let I equal 7, and then I stop. Then I stop and I add those up. And in the process of adding them up, it requires some simplification. Also some knowledge of factorials in this problem. So remember, a factorial is taking every number below it and multiplying. So you go 3 times 2 times 1. So 3 factorial is 6. 4 factorial would be 4 times 3 times 2 times 1, which is 24. 5 factorial is 120. 6 factorial is 720. 7 factorial is 5040. And also, if you had forgotten that one at the start, the 0 factorial is also defined as 1. That's its definition. So now we can add all of these up, and in fact, I'm going to do that real quick, and you can do it on your own if you'd like, but I'm going to type this in my calculator and figure out for us. So I got our decimal of 2.718253968, giving us a long one. You can probably round that to 2.72 and also write it a little bit straighter, not so slanted like that other one. So noticing that example, I started at 0 with my I because the index here, the lower limit said start at 0. So the first thing I put in for I was a 0. And then I moved on 1, 2, 3, 4, 5, 6 until 7, which is where the upper limit told me to stop. What about the second example? Notice now my index is a K, so don't fall in love with the I. It can be really any letter. I, J, K are the common ones to put as the index. But K, which means when I look at the formula, the K is what is changing. Also, where does it tell us to start? At 2. So when I do my first term, it's going to be 1 plus 2 squared, and then plus 1 plus 3 squared, 1 plus 4 squared, and where am I stopping? It says the upper limit is 6, so just one more, 1 plus 6 squared. So I think a point of emphasis here is this 6 up here is not how many terms you're going to have. Because if I count, I have 1, 2, 3, 4, 5 terms, not 6. Okay, so that number up top is not how many terms you have. It's what number is the last number you plug into the equation, the 6. Okay, now we can work through and we can simplify this. So I have 1 plus 4 plus 1 plus 9 1 plus 16 plus 1 plus 25 plus 1 plus 36. Okay, so just taking our time with some nice lovely arithmetic. So 5 plus 10 plus 17 plus 26 plus 37. And this is the easy part of summation notation. We have 15 plus 17, which is 32, plus 26 and 37 gives you 63. And so now I have 95 as my answer to this. So when you see this summation notation, it all equals 95. So it's just good notation where instead of having to write out all of this and say, find that answer, you can write it in a nice slick way like that. And that's kind of the beauty of summation notation, especially as you have more and more complicated functions and sequences and patterns that you need to add up.